In this lesson, we're looking at the gradient function. Now, consider the curve whose equation is given by y equal to f of x. So this curve here, this graph plotted here, is obtained by the function y equal to f of x. Now, if you want to take the gradient of this function, gradient is the same thing as slope. So the gradient or slope of this function, if we represent it with m, is equal to increase in y over increase in x. Increase in x. In other words, the gradient m is equal to y2 minus y1 over x2 minus x1. So from this graph, I have 2 points here, A and B. Point A is as coordinate of x1, y1. That is, if you trace this very point down to x-axis, this side is x1, then trace the same point to y-axis, this side is y1. That is the coordinate of point A. Then coordinate of point B, if we trace it down to x-axis, that should give us x2. Then trace it to y-axis, that should give us y2. So that if we apply it to this gradient, then we are taking a right angle triangle drawn on the secant line. The secant line is this line inside the curve. We are taking the slope of the secant line, not the slope of the curve. So the slope of the secant line is y2 minus y1. That is this minus this, the value there, divided by this minus this. Now, if you set this denominator, which is x2 minus x1, let it be delta x. Let x2 minus x1, if we represent it with delta x, that change in x, then this gradient m, we can write it as m equal to y2 minus y1 over delta x, where delta x is x2 minus x1. Now, if delta x is x2 minus x1, then what if we make s2 the subject of the equation? I have x2 minus s1. Let me write it. It's equal to delta x. If I make s2 the subject of this equation, then s2 is equal to delta x plus s1. Now, if that is the case, we call that the function that we are taking the gradient here is y equal to f of x. So if y is f of x, then we can say y1 is equal to f of s1. So that if y1 is f of x1, then what will be y2? Y2 will be f of x plus delta x, since x2 is, where is it? I made x2 the subject of the equation. So let me first of all write it. Y2 is equal to f of s2, but s2 is x plus delta x. Therefore, y2 is equal to f of x1 plus delta x. Now, if that is the case, back to the gradient, which is m is y2 minus y1 over delta x. Now, we found the value of y2 and the value of y1. So the gradient now becomes f of x1 plus delta x is y2 minus f of x1 over delta x. That is another definition of the gradient of this function. Okay. Now, what if we keep this point A fixed and then begin to shift point B closer and closer and closer to point A? Now, recall the slope we took here, the gradient here is a gradient of this secant line, secant AB. And secant is this line inside the curve. Now, if you draw another line outside the curve, that would be a tangent. For example, I can draw a tangent line at point A. I want to shift point B closer to point A. Now, point B is right here now. What if we shift it down to this place? If I shift it down, as in, this is the point B now. You agree with me now, your x2, the value of x2 now has decreased. This will be the x2, this is y2. Again, if I shift it closer again to point A, let's assume this is the new point of point B now. You can see that x2 now decrease further, y2 again decrease further also. So the point here is as point B gets closer and closer to point A, the gradient of this second line, AB, will be decreasing. So it gets closer and closer to the gradient of the tangent at point A. The gradient of tangent at point A is far, far smaller than the gradient of this second line, as it is right now, because B is at this point. But if we shift B closer and closer to point A, while A remain fixed, the gradient of the second line AB will be decreasing, and it will come to a stage where it will be equal to the gradient of the tangent at point A. So in that case, we can call it the limiting value of the gradient of the line. So let point A remain fixed and let point B move closer to point A along the curve. As B moves closer to A along the curve, delta S move closer or get closer to zero. Why is it getting closer to zero? Look at this is the initial position of point B. But when we shift point B closer to A and place point B here, you can see this is no longer the position for x2. Let me remove the original x2 and show the position of x2. Look at this is the new position of x2. That is if point B shift to this very point. That means value of delta x has decreased because delta x is x2 minus x1. So x2 is getting closer to x1. So when you subtract, the value should be smaller than the initial value. So as we shift point B closer and closer to point A, it will come to a stage where delta S will become zero. That is, if we place point B on top of point A, then there's no more difference between S1 and S2 because both of them are now at the same position. So at that stage, delta S is zero. So as point B gets closer to point A, the gradient of the second line AB gets closer and closer to the gradient of the tangent at point A. So if delta S is made to approach zero, the function m of x, which is f of x plus delta x minus f of x divided by delta x is called the gradient function of y equal to f of x. So as delta s approaches zero, m of x is equal to f of x plus delta x minus f of x over delta x. So this very function here is called the gradient function of y equal to f of x. And how did we get that? By what? Taking the gradient of this second line, AB. Now, that is for y equal to f of x. Now, what if you have y equal to something like s squared, for example? So the derivative of a function, this function here, this curved line AB, and the curved line AB point A, if you trace this point down, this is x1, then trace this point down, this is x2. Then we trace this point to y-axis, this is y1, trace this to y-axis also, this is y2. So if that is the case, from here to here, as from this x-axis to this very point is f of x. Y from x-axis to this point B here, this point here, is f of x plus delta x. Why? We said earlier that if gradient m is y2 minus y1 over s2 minus s1. And if you replace this x2 minus x1 with delta x, s2 minus s1 equal to delta x, then if you make s2 the subject, then that would be x1 plus delta x. So based on what I say here, if I trace this to this point, this is my y2. In other words, from this origin all the way to this point gives us a value of y2. Y from the origin to this very point is y1. So if x2 is x plus delta x, what will be y2 in this case? Since y, what is y in the first place? Y is f of x. So if y is f of x, then y1 will be f of x1. So that y2 will be f of x2, but x2 is x1 plus delta x. So x1 plus delta x. So our y2 here is x1 plus delta x. That is why this line here, this arrow here, let me use a highlighter there. This arrow will denote it with f of x plus delta x because that corresponds to our y2 according to what we have here. That y2 is f of x1 plus delta x. While y1 or y itself is f of x. So from this point to this point is f of x. While from this point to this point is f of x plus delta x. That is equivalent to y2. So if that is the case, then what is y2 minus y1? y2 minus y1 will be f of x plus delta x minus f of x, which is from this point to this point. So now recall that the gradient function of the curve y equal to f of x is given by m1 equal to f of x plus delta x, that is x1 plus delta x minus f of x1 divided by delta x. That is for the function, the gradient of this function, y equal to f of x. Now, the expression m1 is the gradient of the second line, as we learned in the first graph. We got that value by taking the gradient of the second line. This line inside the curve is the gradient of that line, the second line. Now, so if m1 is the gradient of the second line, we said earlier that as b moves closer and closer to a, delta x becomes smaller and smaller, and it tends to 0. So if m2 is a gradient of the tangent at point A, m2 is a gradient of the tangent at point A. Now, as B approaches A along the curve, m1 tends to m2. In other words, as we move point B here, this is the original position of point A. Now, let's shift it down a little. You see that delta x and even y has decreased because the value of x2 now has decreased. Look at the initial position of x2 here. That is when point B is at this very point. This is our x2. But now we shifted point B to this point. X2 has decreased. Shift it down again, S2 will decrease. Y is also decreasing. Y2 is also decreasing. That is why they are saying that as point B move closer and closer to point A, M2 we get closer and closer to M1. Remember, M1 is a gradient of the second line. But if we shift it closer, if we shift point B closer to point A, it will come to a stage where the gradient of the second line will be equal to the gradient of the tangent at point A. So B approaches A along the curve, M1 tends to M2. In other words, the gradient of the secant AB tends to the gradient of the tangent at point A. So we say that M2 is the limiting value of M1 as delta x tends to 0. The limiting value of M1 is M2 because M2 is getting closer and closer. M1 rather is getting closer and closer to M2. M2 is a gradient at tangent, the gradient of the there. If we draw a tangent there and take the slope, of course, the slope is going to be far, far smaller than the gradient of the second line AB. But if you shift point B closer to point A, then the gradient of secant AB will get closer and closer to the gradient of the tangent at point A. We call M2 the limiting value of M1. So M2 is the limiting value of M1 as delta x tends to 0. This limiting value, we can write it as the limit of f of x plus delta x minus f of x over delta x as delta x approaches 0. Now, this limit of f of x over delta x, f of x plus delta x minus f of x over delta x is what we call dy dx. That is the derivative of y with respect to x. Now, the concept of taking the derivative of a function using this approach here, that is taking the limiting value of one the secant line in relation to the gradient of the tangent at point A is called differentiation from first principle. So now that is for f of x. Now what if we have a function like y equal to f of x and you have y plus delta y, that should be f of x plus delta x, such that if I am making delta y the subject of this equation, delta y will be f of x plus delta x minus y. That is, I'm taking this y across equality, the minus y, but y is f of x. I'll just place it as minus f of x. So delta y is f of x plus delta x minus f of x. Now if y plus delta y is f of x plus delta x. Now look at it. From this very point to this very point, that is your y1. In this case, we are not using y1 because our function is y equal to f of x, while the second function is y plus delta y equal to f of x plus delta x. S let with delta x. So when we make S2 the subject of the equation, S2 become delta x plus x or x plus delta x. So that if I have y2 minus y1 original gradient, and this is delta x, so this is y2 minus y1 over delta x. And I know that y2, if I have my y1 to be f of x, my y2 should be f of x2. But my x2 is what? Look at it here. If I move this across the equality, s2 is equal to s1 plus delta x. So this is plus delta x. So in this case, from here to here, which is of course your y2, now become y plus delta y. That is here. Then the difference between this line and this other line, which is from here to here now, will be delta y. So that if you take the gradient of this secant line here, gradient is this divided by this. So the gradient of this secant line will be delta y over delta x. So that, again, if you keep point A fixed, y will shift point B closer and closer and closer and closer to point A. The gradient of the secant line will be approaching the gradient of the tangent at point A. So since the gradient of tangent at point A is fixed and is smaller than the gradient of the secant AB, then we see the gradient of tangent at point A as the limiting value of the gradient of secant AB. So that if I call this delta y over delta x as my m1, then my m2 will be limit of delta y over delta x as delta x approaches 0. As delta x approaches 0, then it's called dy dx. So we use this to differentiate function from first principle. The technique adopted in finding the derivative of a function from the consideration of the limiting value of a function is called differentiation from first principle. So we have some examples here. The first one says find the derivative of f of x equal to s squared from first principle. Okay, so if f of x is equal to s squared, now our goal when taking derivative from first principle is to try to express the gradient of this function in this format: f of x plus delta x minus f of x over delta x, and then take the limit of this. The limit of this will give us the derivative of this function from first principle. So if f of x is x squared, what will be f of x plus delta x? F of x plus delta x squared. And x plus delta x squared means x plus delta x times x plus delta x. So we are going to expand this. So this will be x plus delta x. X times x is x squared. X times delta x is x delta x. Now, one common mistake that students make is to multiply this x with this x here. This x is attached to delta x, so you can't multiply with this x here. This x here, you cannot multiply with this and say it's delta x when no, that is wrong. This x and delta x are together. They are not separate entities. So you cannot multiply this by this and call it x squared. That would be wrong. So instead of delta x squared, it is x delta x. That is the point I'm making there. Now delta x times x, again, is x delta x. Then delta x times delta x is delta x squared. When you can say I put the delta x squared in brackets, that is square. This delta x is a single variable in this case. And that is the reason why you cannot multiply this x by this x. Okay? So in this case, this will be x squared plus x delta x plus x delta x is 2x delta x. Then plus delta x squared. So it's f of x plus delta x that give us this. F of x, let me write it. F of x plus delta x give us that. Now, recall I said earlier that whenever you are taking derivative from first principle, your goal is to try and express the derivative of that function in this f of x plus delta x minus f of x divided by delta x. So we are trying to arrive at this and then take the limit of reciprocal. So in this case, now I have f of x plus delta x equal to x squared plus 2x delta x, f of x plus delta x minus f of x. That would be x squared plus 2x delta x plus delta x squared minus, what is f of x? F of x is x squared. So as I subtract f of x on the left hand side, I have to subtract it on the right hand side too, because I'm trying to arrive at that first principle derivative of first principle. So minus x squared here, so that this will go. That means f of x plus delta x minus f of x is equal to 2x delta x plus delta x squared. And the last stage, again, what we are trying to arrive at is this. Let me write it here so I don't have to clean it again. F of s plus delta x minus f of x. Now we have f of x plus delta x minus f of x here, which is equal to 2x delta x plus delta x squared. So the next thing now is to divide both sides by delta x here, so that we can arrive at something like this. So f of x plus delta x minus f of x divided by delta x is equal to 2x delta x plus delta x squared divided by delta x. Since delta x is common to both of them, let's factorize it out. So delta x into 2x plus, now I have delta x squared here, but I factorize it now. So I'll be left with only one delta x here, then divided by delta x. So this delta x can cancel this delta x. So I have f of x plus delta x minus f of x divided by delta x is equal to, and finally, the limit of f of x plus delta x minus f of x over delta x as delta x approaches 0 is equal to, if I take the limit of this, the limit of sum is equal to sum of the limits. That is one of the properties of limit we learned in our previous lesson. So limit of 2x plus delta x, and then that will be limit of this sum. Limit of 2x is as delta x approaches 0, so that this becomes 2x. Therefore, the derivative of f of x equal to x squared is 2x. Okay, that is the first example. The second example is to find the derivative of y equal to x to the power of 3 from first principle. Let's make some room on the board, work on that. So if y is x to the power of 3, so if y is x to the power of 3, what will be y plus delta y? Y plus delta y will be x plus delta x to the power of 3. And x plus delta x to the power of 3, that means we are going to multiply x plus delta x, we multiply it by itself up to 3 times, plus delta x, then times x plus delta x. Now from the previous example, we already know this multiplied by this, and that gives us x squared plus 2x delta x plus delta x squared. That is for these two products now, but we still have one more here, so multiply by x plus delta x. X squared times x is x cubed, so this will be x cubed, then x squared times delta x is x squared delta x, then 2x delta x times x is 2x squared delta x. Why 2x delta x times delta x is 2x delta x squared. And see what I'm doing? Delta x will multiply itself. Why x multiply itself? I cannot multiply this x here by the x here. Delta x is a single variable on its own. So you can't multiply the s attached to 2 with the 1 attached to delta. That is the point I'm making. So this is 2s delta s squared. Then finally delta s cubed multiplied by x is s delta x delta s squared. And delta s squared multiplied by delta, that will be delta s cubed. Now let's collect like terms, anything that is carrying the same power. So this will be s cubed here. This s squared delta and 2s squared delta can be added. Why? Because this has s squared and delta, 1 delta. This also s squared and 1 delta. So we can add them together. So s squared plus 2s squared delta, that is s squared delta rather, plus 2s squared delta is x. What I did here is like saying 1x squared plus 2x squared, that is 3x squared. Then delta x. Then plus, again, this and this can be added because this is 2x, this is 1x. This is delta x squared, this is also delta x squared, so we can add it together. And 2x plus x is 3x. So that is 3x delta s, 3x delta s squared. And plus the last one, which is delta s cubed. Okay. So that is y plus delta y plus delta y that give us this expansion now. And what will be delta y? Because I said earlier that to take derivative from first principle, when the function is a function of y equal to like this, your goal is to try and express delta y over delta x. So we are trying to arrive at this. So in that case, I want to make delta y the subject of this equation. And I'll do that by moving y to the other side. So my delta y becomes s cubed plus 3s squared delta x plus 3x delta s squared plus delta s cubed minus y. This y here. Just move it across equality is plus y here, but when it crosses equality, it becomes minus y. But from the function given to us, y is equal to x to power 3. Y is equal to x to power 3. I'll just put x to power 3 there. So that this x to power 3 minus x to power 3 is gone. Therefore, delta y is equal to 3x squared delta x plus 3x delta s squared plus, I wrote 2 here instead of 3. This delta s cube, please. Plus delta s cube. Now, the delta y over delta x, factorizing delta s. I have delta x into 3x squared. Because once I bring delta x out, there's no more delta x here. Because we are dividing through by delta x. That's the meaning of factorization. If we divide this term here by delta x, this delta x will become then plus 3s. I have delta s squared here. If I divide it by delta x, I'll be left with only one delta. So this will be 3s delta x. Then this delta s cubed, if we divide by delta x, we'll be left with delta s squared. Divide both sides by delta x. And this delta x can cancel this delta x. So that delta y over delta x, delta y over delta x is equal to 3x squared plus 3x delta x plus delta x squared. And limit of delta y over delta x as delta limit of this function 3x squared plus 3x delta x plus delta x squared. This will be 0 because we have delta x there. Because delta x is approaching 0. That is, we substitute 0 here. 0 times 3x is 0. Again, 0 squared is 0. So our answer is 3x squared. So the limit of delta y over delta x is 3x squared. And that is the derivative of y equal to x to the power 3 from first principle. And the next example says, find the derivative of y equal to 1 over x from first principle. Let's get some space on this board. Okay, so if y is equal to 1 over x, and we want to take the derivative from first principle, then what will be y plus delta y? That should be 1 over x plus delta x. Now, making delta y the subject of this equation, delta y will be 1 over x plus delta x minus y. That is, I move this y across equality and it becomes minus y here. But y is 1 over x. So instead of writing minus y then, let's replace it with 1 over x. So minus 1 over x. So that we can solve this fraction, LCM of x plus delta x, and x is x plus delta x times x. Then we put the s in front. So that by this, that is, if I divide this LCM by this x plus delta x, look at this. Can I do that? X times x plus delta x, x. This will cancel this, so I'll be left with x. So this LCM divided by this is x. Now x times 1 is x. Then the LCM divided by this x is x that will be cancelled, while x plus delta x will remain. Look at it. X times x plus delta x divided by x. X cancelled. Then we are left with x plus delta x. I'm just solving a fraction, just like we used to do in normal fraction. If I have 1 over 2 plus 1 over 3, for example, I need to look for LCM of 2 and 3, which is 6. Then to solve the fraction, I divide 6 by 3, by 2 here, which is 3. 3 times 1 is 3. Divide 6 by 3, which is 2. 2 times 1 is 2. And then the fraction is solved like that. It's the same thing I'm doing here. So LCM of x plus delta x by x. Now take that LCM, use it to divide this denominator, whatever is the answer, use it to multiply the numerator. Do the same thing here. That is exactly what I'm doing here. So this will be minus x plus delta x. So delta y is equal to that. Okay, now let's open up these brackets. So this will be x minus x as this minus over x times x plus delta x. Now x minus x is 0, which means delta y is equal to negative delta x over x times x plus delta x. Now dividing both sides by delta x will be negative delta x over x times x plus delta x divided by delta x. I intentionally use division instead of over so I can point out what I want to point out there. I'm dividing by a fraction, and when you divide by a fraction, the sign of division will change to multiplication. So this delta y over delta x is equal to negative delta x over x times x plus delta x. This is x here. Don't know what is wrong with my name. Times 1 over delta x. This division changes to multiplication. Then we multiply by the reciprocal of this fraction. So delta x divided by delta x, 1. Therefore, delta y over delta x is equal to negative 1 over x. Let me just open up this bracket. X times x is x squared plus x delta x. Now limit of delta y over delta x as delta x approaches 0 is equal to, well, this will be 0 since delta x is approaching 0. Remember, limit of the quotient, you take the limit of the numerator, the limit of the denominator. So if I take the limit of this denominator, limit of x squared is x squared as long as it's delta x that is approaching 0. The limit of x delta x is 0 because delta x is approaching 0. Therefore, our derivative of y equal to 1 over x is what? From first principle. Then the next one says find the derivative of y is equal to c, where c is a constant from first principle. So if y is equal to c from first principle, and we are to take the derivative of this, and they say c is a constant. Derivative is the rate of change of one thing with respect to another thing. But if c is a constant, it means it's not changing. Therefore, if y is equal to c, y plus delta y is still equal to c. Why? Because c is not changing. They say c is a constant. Now, making delta y the subject, delta y should be equal to c minus y, but y is equal to c, therefore that will be c minus c, which is 0. The c minus c is 0. And delta y over delta x is equal to 0 over delta x. 0 divided by anything is 0. The delta y over delta x is equal to 0. The limit of delta y over delta x, derivative of a constant is 0. Okay, that is an important thing you need to take into. Derivative of a constant is 0. Then the last one here says from first principle, find from first principle the derivative of y equal to ax plus b, where a and b are constants. Okay, if y is ax plus b, that means y plus delta y will be a times x that is changing. A and b are constant. Okay, then plus b, I forgot the plus b there. So delta y plus delta y is equal to a times x plus delta x plus b. So that if I open up this bracket, that will be ax plus a delta x plus b. If I rearrange that, I have ax plus b plus a delta x, making delta y the subject of the equation. Remember, it's y plus delta y that gave us this. So making delta y the subject, delta y will be ax plus b plus a delta x minus y. But y is as plus delta b. So instead of putting y here, let's just substitute it with its value, which is as plus b minus ax plus b. So that when we open these brackets, we are going to have ax plus b plus a delta x minus ax minus b. So this can go as ax minus as 0 and b minus b also 0. Therefore, delta y is equal to a delta x. Dividing both sides by delta x, delta y over delta x is equal to a delta x over delta x. So delta x can cancel. Therefore, delta y over delta x is equal to a. Taking the limit of delta as delta x approaches 0 is equal to the limit of a constant is a constant itself. Therefore, dy dx is equal to a from first principle. Therefore, the derivative of ax plus b is equal to a. Okay, that is all for differentiation from first principle.